Welcome back to Learning with Merit. We're going to talk about floating point or flop errors in this one. So floating point errors result from the way that computers do math and store values. And because binary is base 2, there are errors that can occur when performing certain types of floating point operations. So here is an excellent example. Here we have a double called 0.3, which is the sum of 0.2 and 0.1. And when we look at this, we're checking if system out print not 0.3 equals 0.3. Now math will tell us, right, our understanding of mathematics will tell us that 0.2 and 0.1 should result in an answer of 0.3, but we're going to see false in what we're looking at. So if we run this code real quick, okay, let's make sure that we save our code real quick and then run it. All right, here we go. So we end up with false for this Boolean expression right here, which doesn't make any sense to us as people who understand math. And then I printed out the value of 0.3 here for you. And you see it's 0.3, a whole bunch of zeros, and finally a 4 there at the end. And that is interesting because what sense does that make? How do we end up with 4? How do we even round to that 4 with all of these zeros or whatever's going on here, right? Well, let's think about it. You need to pay attention to this because of this thing right here. If you're using a comparison operator with floating point numbers, you may end up with an unintended error. So it's not always the best idea to try to do floating point math with computers. It's funny because people will often say computers are really good at math, right? But they're not good at math. Okay? They're designed to do operations well, right? But that doesn't mean that they're good at math. People are good at math, you know. So let's take a look here. Decimal versus binary values when we're dealing with this. So here we have two lists. I have the decimal places on the top, decimal meaning base 10, and then I have binary meaning base 2 down here on the bottom where we keep the decimal in the middle. So we all remember this from school, hopefully. The ones place, tens, hundreds, thousands, 10,000s, right, so on and so forth. And I actually end up missing a 0 there, which we can add, which throws everything off just a tad, right? But here's the point. When we look at this, we have the same places in binary. And they're just different values. And especially when we look at the fractional places, so 1/10, 1/100th, 1/1000th, 1/10,000th, so on and so forth, right? If we look at this, though, what you'll see, it's 1/2, 1/4, 1/8, 1/16th, 1/32nd, 1/64th. It's not easy for the computer to represent these values, tenths, right, in the same way that we would represent tenths in our decimal values. And so here's another good example of how we might deal with this. If we look at 0.2, that's 1/5 in decimal. It's simple. You place a 2 in the 1/10th place, right? 0.2 in binary is more difficult. How do you get 2 by placing ones in the binary places? Well, we run into an issue, right? 1/5. None of these really work. So we're gonna have to skip 1/2 because it's not that big. We're gonna have to go to 1/4, but skip that one because it's not that big. So now we're gonna have to deal with the 8ths places, right? And what we run into is it's a similar problem that we deal with when we do 1/3 in decimal. We end up with 0.33 repeating indefinitely, right? And it's because it's not easy for our system, our decimal system, to represent 1/3 of something, right, in the way that we write our math. It's the same thing in binary. So the same issue exists in binary. It ends up with this infinitely repeating value, 0011, 0011, 0011, forever. And because of that, because the value is infinitely repeating, what we end up with is the issue of the computer eventually has to come up with a place where it decides to stop. So what we end up with is a value that's very, 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 very close to the right answer, but with a little tacked on piece at the end because of this infinite repetition. Let's look at some other examples that there are. Here's one right here, 0.4 and 0.1. Let's go ahead and run this. Let's see what we get. So if we do 0.4 and 0.1, right, it pretty easily comes out when we add it together, we get 0.5. But when we subtract it, we get the 3,0,0,0,0,0,4 problem again, right? When we do 0.7 and 0.1 and we add them together, we get 0.79999999999. But if we subtract it, we get 0.6. All right, let's add another one to it. And of course, you can see the binary representations of these two values here and sort of how that works. Because the math is being done on the binary representations, because that's how the computer stores the values. Here's another one. We've got 0.9 minus 0.1 and 0.9 plus 0.1. Let's see what we get out of that. So if we come down here, this one actually works out for us. So we got 0.9 minus 0.1, we get 0.8, and then 0.9 plus 0.1, we get 1. So in some cases it works. So these errors are caused by rounding error when the Java compiler compiles the program, right? You got this infinitely repeating number, so it rounds, and it does it incorrectly, right? But it rounds because it has to cut off the value at some point. So it's not a bug. It's not, and it shows up in other languages too, right? But it's inherently a problem with how we use numbers and how we work with them, right? And we all know, for example, if you do 0.33 repeating forever, and 0.33 repeating forever, and 0.33 repeating forever, right? 1/3 plus 1/3 plus 1/3 should give us 1, right? But the problem is, how do we actually get there? Can you actually prove the answer to that, right? And maybe some of you can. But the point is that it's really hard to understand how 0.333, something that eventually in our mind would be 0.999999999 forever, is actually the value 1. Okay? It's the same issue with the computer. Okay? So floating point errors are something we need to watch out for and actually learn how to deal with. There are some options that you can use for dealing with floating point errors. One of them is to review significant figures and round, right? So if you have learned about significant figures in some of your other classes, this is how many decimal points you actually need in the number, and round. For example, if we cut off or round some of these values, we end up with the answer we're looking for. You could also do integer math. This is another interesting way of dealing with floating points. So because we can effectively just remove the decimal point and then place it back, we could remove the decimal point, do the math, and then bring the decimal point back. And that would give us the correct answer. And so that's another clever way of dealing with floating point errors. So I hope you learned something, and thank you for watching Learning with Merit.